In this section, we will talk about the effect that saturation of the detector has upon calibration. Most analytical detectors at some point will begin to show the signs of saturation, quenching, or self-absorption of the response when the detector is overloaded. In this slide, we have attempted to illustrate how susceptible the more commonly used environmental detectors are in regards to saturation. The easiest way to determine if saturation is being encountered is to review a plot calibration curve for the analysis. In this example of actual data from EPA method 8260B analyses of standards show the characteristic of flattening of the response as saturation is encountered with the higher concentration standards. Other signs of saturation of the detector with organic analyses can be the presence of a reverse tail or rise on the front part of the peak, and by the change in the ratio of the ions observed. In this case, the observed actual percent ratio of the secondary ion presence is lower than the expected percent ratio. Another sign of saturation can be the presence of a flat top peak, as is shown in this example, and again by the decline or saturation of the secondary ion compared with the expected percent recovery. One acceptable way of dealing with saturation is to drop the higher concentration standards that are affected by the saturation of the detector. In this example with acetone, when the two highest calibration standards are dropped, the calibration fit line represents the points better and drops the relative standard deviation from 28.8% to 14.9%. Another acceptable way to handle a small amount of saturation of the detector would be to change the calibration fit to a nonlinear calibration model, such as quadratic. We stress that this may only be used with small amounts of observed saturation. In this example with the chloromethane curve, a small amount of saturation can be observed with the higher calibration points. These points, however, still have substantial increase in their response ratio compared to the previous lower calibration point, and accurate quantitation of samples can occur if the proper calibration model is utilized. In this case, when the calibration model is changed to quadratic, it shows that the points are now well represented. 8000C in the Arizona regulations, however, contains the EPA statement of intent to not allow nonlinear curves to be used to compensate for the detector saturation. Arizona believes that this statement does not preclude the use of quadratic curves for situations similar to that of the chloromethane curve that was just presented, where very small amounts of detector saturation are present. We believe that the EPA's intent for this statement is because of the problems encountered as shown in the following 4 examples. In this actual example of a calibration plot for vinyl chloride by EPA method 524.2, a saturated high standard response is inappropriately included in the calibration plot, which formed a parabola when a quadratic model was applied. In another actual example, another lab was using a cubic or third order curve forming a parabola for analyzing samples for diesel C10 through C32. The highest calibration point has a reduced response due to saturation. If this curve was not visually reviewed, the R-squared value of 0.998 would make it appear acceptable. The final organic example of detector saturation is with the compound fluorine from an EPA 8270C analysis, where the highest calibration standard has had its response saturated to the point that it is actually lower than the previous lower concentration point. Saturation, as previously mentioned, can also be observed in metals analyses. In this example, from a flame atomic absorption analysis, a quadratic curve was utilized by the lab to accommodate the saturation of the responses from the calibration standards. The quadratic curve fit makes the correlation coefficient appear to be perfect, even though the accuracy of the curve at the higher end would be questionable.